Hello everyone, happy Tuesday. I'm so sorry that I can't make it to class, but let's get through section 9.3, exponential functions, and section 9.4, logarithmic functions. Alright, first things first, an exponential function is a function that's increasing or decreasing by a common ratio. And what that means is that we are multiplying or dividing, but we like to say multiplying mostly, to get from one term to the next. Okay, let's look at some examples here. We've got an example of exponential growth. And I'm going to show you kind of a basic graph here. Actually, I'm going to do decay first, and then exponential growth over here. The function we'll use f of x equals 1/2 to the x power. Notice the exponent is the variable. We could graph this by plugging in some values like -2, -1, 0, 1, and 2. 1/2 to the negative second is 4. 1/2 to the negative first is 2. 1/2 to the 0 is 1. 1/2 and 1/4. So -2 over 4 up. -1 over 2 up. 0, 1/2. I'm sorry, 0, 1. 1, 1/2, 2, 1/4. And one thing you'll notice is that this graph is decreasing from left to right. It's going downhill. Also, you'll notice that this graph never crosses the horizontal axis. That's because exponential functions have a horizontal asymptote. It's a restriction on those range values. So this is an example of exponential decay. The graph is decaying left to right, and we have an asymptote right here. Let's look at an example, a pretty basic example of exponential growth. We're going to use the function f of x equals 2 to the x power. We could plug some values in here. Let's do -1, 0, 1, and 2. 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. We can graph this. And you'll notice kind of the same pattern, except for this time the graph is growing from left to right. But the same situation is true about the horizontal asymptote. There's no y values below 0. So these are basic patterns for exponential graphs, okay? Decay, downhill left to right. Growth, uphill left to right. And all exponential graphs are going to have some kind of asymptote, which we'll talk a little bit about on the next slide. Here's the basic form of the equation of an exponential graph. It looks like this. F of x equals a times b to the x minus h plus k. Let's talk about what all of this stuff means, okay? A is indicating a stretch or a shrink in the graph. Also, if there's a negative in front of A, that indicates there's a reflection. B is the base. That's that common ratio that we change by. There's a growth function if the base is greater than 1, and a decaying function if the base is in between 0 and 1. X minus h indicates a horizontal shift, kind of like we saw with other functions. X plus h indicates a shift left h units. x minus h indicates a shift right h units. And then last but not least, the plus k on the end indicates a vertical shift. So we'd go up k units and down negative k units. So this is the basic form of that equation, an exponential equation, which kind of helps us understand how the graph can move around. One thing we kind of want to talk about right here is that this k value is the vertical asymptote. It's located at y equals k, which is a horizontal line at whatever that k value is. Let's just get a little look at this. What is the graph going to look like? If it's positive, that means A is positive, and the graph is going to be above that horizontal asymptote. Above the horizontal asymptote. So we could see it looking like growth, increasing left to right. What about a positive A value, but it's decaying? That function's still going to be above the horizontal asymptote, but just decreasing left to right. Remember, growth is when the base is greater than 1. Decay is when the base is between 0 and 1. If the graph is negative, that's when A is negative, and what that means is that the graph will be below the horizontal asymptote. So, horizontal, you can think about it as just a reflection of this graph we have right here, just over, looking like this. Same thing over here. If that A is negative, it just reflects over. And you can see that now this is growth and this is decay. So once you add that negative A value and do a reflection, what was growth becomes decay, and what was decay becomes growth. Let's graph this and then find the domain and range. All right, so what could be helpful is that we can make a table, and then you could shift after if you want. So if you would like to graph y equals 1/2 times 4 to the x, then shift down 6. That can work because I see that -6 there. That could be a little bit helpful to you if you hate building a table. If you don't mind, you can do everything all at once. It's up to you. So I'm going to do the shifting because I like to plug in easy values like -1, 0, 1, and 2. If you shift down, you might have to, down, left, or right, you might have to adjust the values you plug in. 1/2 times 4 to the -1st is 1/2 times 1/4, which is 1/8. Okay. 1/2 times 4 to the 0 power is 1/2 times 1, which is just 1/2. For 1/2 times 4 to the 1st is 1/2 times 4, which is just 2. And 1/2 times 4 to the 2nd is 1/2 times 16, which is 8. So we can go plot these points, -1/2, 1, -1, 1/8, 0, 1/2, 1 over 2 up, and then 2 over 8 up. But that's without this transformation right here. We can bring that in second. So we know we have a horizontal asymptote at y equals 6. And now we can just drag all of these points down 6 units if you would like. So 1, 2, 3, 4, 5, 6. It's now at -4. And 8 minus 6 is 2. And we can just bring down 6. 1, 2, 3, 4, 5, 6, and 6. And then there's that final graph. The domain of exponential functions is always going to be all real numbers. And the range is going to depend on that horizontal asymptote. In this case, y is always going to be greater than -6, not equal to. Let's look at another one where we've got a little bit more going on here. Here you can see we have a reflection with that negative in front. We have a shift to the left 2, and we have a shift up 5. So we've got a lot going on here. In this case, it might be a good idea to graph the function f of x equals 1/3 to the x, or even -1/3 to the x, then do the 2 left and up 5 after. That's what I'm going to do. You can decide how you want to break it down. But if you start shifting left 2, then you're going to have to move your x values a little bit, otherwise you might get some weird values. So that's why I would just prefer to do it this way. I'm going to use the values -1, 0, and 1. Negative, and I'm doing -1/3 to the x here. -1/3 to the -1 power is equal to -1 times 1/3 to the -1st power, which is -1 times 3, which is -3. -1/3 to the 0 power is -1. And -1/3 to the first power is -1/3. So -1 over down 3, 0 over down 1, and 1 over down -1/3. So this before these transformations have happened, the 2 left and up 5. I know I have a horizontal asymptote at 5, so I can go draw that in. And now I can just shift the points. Left 2, 1, 2, up 5, 1, 2, 3, 4, 5. Left 2, 1, 2, up 1, 2, 3, 4, 5. Left 2, 1, 2, up 1, 2, 3, 4, and 5. And there you can see that graph. So sometimes it's easier if you graph just the basic exponential function and then perform the shifts after. All right, go ahead and pause this problem. You try. Unpause to check your answer. All right, so I went ahead and I graphed 2 times 3 to the x, and then I performed that shift of down 9 based off that horizontal asymptote being at -9. And that's what the graph should look like. All right, so now we're going to do some writing of equations. It says write the equation of an exponential function that has a base of 4 and has been shifted to the right 7 down 9. Remember what the basic form of our equation looks like. All right, so it has a base of 4, so b is 4. Shifted to the right 7 means x minus 7. Down 9 means minus 9. We could throw f of x in front. And write the equation of an exponential that has a base of 5, so b is 5. Has been shifted left 2, so it's going to be x plus 2. Up 8 is plus 8. And vertically stretched by a factor of 4 means multiplying by 4 in the front. So we're just using the basic form of our equation and what we know each variable stands for to write the equation. In context, exponential equations can be used to find compound interest. There's a formula that goes along with that. It looks like this. A equals P times 1 plus R over N to the NT. Let's talk about what all of this means. Compound interest is talking about money made over time. So A is that final amount. Okay. P is that principal or beginning amount. Okay. R is your interest rate. Make sure it's expressed as a decimal. And n is the number of times compounded. Per year. So basically that's like the number of times your interest is assessed on an account. So for instance, here's some examples. If your interest was looked at annually, n would be equal to 1 because that's one time a year. If it was semi-annually, n would be equal to 2 because it's looked at twice a year. If it's quarterly, n would be equal to 4 because that's 4 times a year. Monthly, n would be equal to 12 because there's 12 months in a year. Weekly, n would be equal to 52. And daily, n would be 365. All right, let's look at some examples. You invested $500 at 2.2% interest, compounded quarterly. How much would you have after 2 years? Let's use our formula. I'm going to write it right here in case you forgot. Not Y, sorry, A. Okay, and so our amount would be the initial, which is 500, times 1 plus our interest rate, 0.002. Make sure you write it as a decimal. Not 002. 022, sorry. Over compounded quarterly, n would be 4 to the n. T. T is time in years, so that's 2. I would just plug that into my calculator and we'll get out 522.43. After 3 years, we rinse and repeat the same process. But instead of 2, we use 3. And we would get, I actually don't know what the answer is. Something a little bit more. And after 9 months, the only difference is that 9 months is 9 out of 12 because time is in years. This is 0.75, 75% of a year. So we use the same formula. 1 plus 0.022 over 4 times 4 to the 0.75 power, and you'll get $508.30. So this is an example. Many things are modeled by exponential equations in life, but compound interest is something that's commonly modeled by exponential equations. We're going to get into the second part of the lesson, which is logarithms, okay? Logarithms are the inverse of exponential functions. Okay, so y equals b to the x is like a very basic exponential function. Its inverse is log base b of y equals x. So we can rewrite logarithms as exponential functions and vice versa to help us solve and understand them. Okay. It says rewrite in logarithmic form. So remember, y equals b to the x is the same as log base b of y equals x. Here's how I think about it. Log base b is 9 of the answer, 729, equals 3. When you look at the log version, you should be able to rewrite it 9 to the third equals 729. That's how you double check. Let's see the next one. Log base 3, 1 over 81 equals negative 4. To check, 3 to the negative 4th equals 1 over 81. E is just a natural number. We don't need to worry about it. It's just a number. Log base E 7.5 equals 2. Again, e to the second equals 7.5. And last but not least, log base 7 of 49 equals 2. Check 7 to the second equals 49. Perfect. All right, now let's rewrite each exponential log in exponential form. This is where that little circular motion helps. 3 to the second equals 9. 25 to the first equals 25. They're just inverses of each other, so it's just different ways of writing those inverses. It says evaluate without a calculator. Okay, we can do that if we can rewrite these things. We can just set something equal to x and rewrite it in its exponential form to help us. 2 to the x equals 64. I can do that in my head or use my calculator. X equals 8. 8 to the x equals 2. And I'm like, okay, well, I know 2 to the 8th, 2 to the third is 8. So that means this is the cube root of 8 equals 2. And I express the cube root as a rational exponent, which is 1/3. 3 to the x equals 1 over 27. I know 3 to the third equals 27, but 1 over 27 means that x has to be negative. And last but not least, over here, 1/2 to the x equals 16. I know 2 to the fourth equals 16, so 1/2 to the negative fourth has to equal 16. One thing to remember is that if you don't see any number here, then the base is 10. If no base is stated. This is called the common log because although all exponential functions can be written this way, it's common in nature and in modeling to use base 10 for the logarithmic functions. All right, let's do a little more of rewriting these things. Right here we've got, we can set this equal to x just like we did on the last page. 3 to the x equals 3 to the fifth. Bases are the same, so exponents are equal. So if you notice, when the bases are the same, base of the log, base of the exponent, they cancel each other out. Right over here, we could do the same, but the bases are the same. So they cancel, and I'm just left with 9. Here the bases aren't quite the same. Log base 4 of 16, I can find out what that is. 4 to the x equals 16, x equals 2, and then I've got 1/4 times 2 right here, which is 1/2. So I had to break that one down a little bit more. Here the bases are the same, they cancel, x equals 15. We're going to stop right there and we'll save graphing logarithmic functions and any questions you have for Thursday's class. Have a great day. Bye.